The same questions I always ask myself are, what does it all mean? What is it all about? But in the context of science, I'm interested in what the world is made of, how the universe began, where it's going, and what can we do while we're around here. And in my case, that means studying quantum mechanics, the theory of how things behave at their most fundamental level. And now, 25 years ago, I started working on the problem of quantum computing, which was how atoms and molecules, photons, elementary particles process information. At that point, there were only half a dozen people in the world looking at this problem. And now there are thousands. There goes the neighborhood. So, but in any field that expands by so much, so rapidly, there are now all kinds of branches on this tree. And there's still the branches of the kind of the fundamental questions of how we understand the world in terms of how it processes information. Interestingly, right now, there's been a resurgence of interest in ideas of applying quantum mechanics to ideas and quantum information to ideas of quantum gravity and what the fundamental theory of the universe actually is. Turns out that quantum information has a lot to offer to people who are looking at problems of, for instance, what happens when you fall into a black hole. And by the way, my advice is don't do that if you can help it. So if you fall into a black hole, does any information about you ever escape from the black hole or not? And these are questions that people like Stephen Hawking have been working on for decades. And it turns out that quantum information has a lot to give to answer these questions. Then there are a lot of practical questions about understanding what's going on in nature. For instance, it's become clear over the last decade that in photosynthesis, where a particle of light comes into us from the sun, is absorbed by a chlorophyll molecule, the energy rattles around inside a leaf, gets turned into more leaves. Photosynthesis is operating in a very quantum mechanical fashion, and actually just exactly the same kinds of models that we use to look at quantum computation allow us to understand what's happening in photosynthesis. Turns out that photosynthetic plants and bacteria and algae are extremely sophisticated in the way they use quantum mechanics. They use quantum coherence and funky effects like entanglement to get very, very high efficiencies of energy transport. Basically, my motto about this is, okay, if a little quantum hanky-panky will allow you to reproduce a little faster, then by God, you're going to use quantum hanky-panky. And it turns out that plants and bacteria and algae have been using quantum hanky-panky for 1 billion years to make their lives better. Indeed, what's happening in quantum information and quantum computing is that it's become more and more clear that quantum information is kind of a universal language for how nature behaves. A few years ago, there was a centerfold in Physics Today, the journal for physicists for the American Physical Society. Now, it wasn't a very sexy centerfold. It was a centerfold that had all the different parts of physics, like high energy physics and solid state physics, string theory, physics of mechanics, nanophysics, and right in the middle they put quantum information. And the reason was that this centerfold showed which parts of physics were talking with which other parts of physics. So who in this field was talking with this other field. And they had to put quantum information right in the middle because everybody was talking with the people in quantum information. So physical chemistry, or physical chemists are the people who study photosynthesis. All of a sudden, all the physical chemists were talking with people like me. And we were doing experiments on, plants and bacteria. Now we're actually doing artificial experiments where we try to make artificial, in our case, they are systems, women and virus-made systems that mimic the high efficiency of energy transport and photosynthesis. And in fact, by using ideas from quantum information, we've constructed systems that do much, much better than even the most efficient, naturally occurring system. So, and at the same time as there are all these theoretical developments, there have been major advances in how you build devices that process information and building quantum computers. So there's a company, D-Wave, that builds these special purpose quantum computers that are not general purpose quantum computers that could, break codes and strike fear into the heart of the NSA, assuming, of course, the NSA has a heart. These systems are up and running, and people are buying them and trying to figure out if they can solve hard problems faster than classical computers. The jury is out on this question. We don't know if they can or not. At the same time, people building superconducting systems and systems made of atoms or ions and optical systems have gotten much better at building quantum computers. So we expect in the next 5 to 10 years to have quantum computers which are large enough to do things no classical computer could ever do. So this is actually a very exciting time in quantum computation for coming up with stuff to do with quantum computers. There's an old idea, it was originally due to Richard Feynman, that you could use quantum computers to simulate other quantum systems, kind of a quantum analog computer. And then I wrote the first algorithms 20 years ago. I wrote the first algorithms for how you could program the quantum computers we have now to actually explore how other quantum systems behave. And in the next few years, we're going to have devices that will allow us, to build quantum mechanical simulations of, say, what happens inside a black hole. We can look at what these models actually do. A few years ago, some friends of mine and I used a small quantum computer to simulate what happens in the process of time travel, because the theory of time travel is intrinsically quantum mechanical. And if you want to find out what happens when you send a photon a few billionths of a second backwards in time and have it try to kill its former self, well, we have an experiment that tests to see what happens when you do that. Actually, may I say that in this case, it's lucky that there's no Society for Prevention of Cruelty to Photons, because a lot of photons died in that experiment. But it turned out the one photon that tried to kill itself in the past always failed, because our quantum theory of time travel shows that you can't go back and do something self-contradictory in the past, like kill your former self. One of the most fun applications of quantum computing right now mirrors what's happening in classical computing. So amongst the biggest advances in classical computing these days are programs for machine learning, to take computers and have them process humongous amounts of data and figure out what the patterns are. The NSA uses this to spy on us. Google uses it to spy on us. Amazon uses it to spy on us. Everybody uses it to spy on us. But in machine learning, it's no secret we live in an era of big data. Human beings are generating Avogadro's numbers worth of bits every day or so. And so, and companies like Google and Amazon and Microsoft are processing this data to try to find out every aspect of their life so they can sell us stuff. Computers are getting very good at processing data and finding patterns in it. So now quantum mechanical systems have this feature that they can generate patterns that's very hard for any classical system to generate. And it also turns out that quantum computers can actually detect patterns that it's very hard for any classical computer to generate. It also turns out that quantum computers can detect and identify patterns that are very hard for a classical computer to detect. So for example, if you have a huge data set, like the tick-by-tick history of all the stocks on the Dow Jones for the last 50 years, it's a big data set, and you want to say, well, I'd like to process this to find out what a good portfolio would be for me if I can tolerate a certain amount of risk and I want to have a certain amount of return. Well, then with a pretty small quantum computer, the kind that we're going to have in the next 5 years or so, you could actually find the answer to that question much more accurately than you could do on a classical computer. So quantum computers work by storing and processing information at the most microscopic level. So for instance, if you have an electron, you could call electrons spinning up like this 0. You could call electrons spinning like that 1. And you could call electrons spinning like that 0 and 1 at the same time, which is the primary feature of quantum computation. Quantum bit or qubit can be 0 and 1 at the same time. And this is where quantum computers gain their power over classical computers. So for the last 20 years or more, my colleagues and I have been working to build quantum computers using electrons, using particles of light. So, a photon with its electric field wiggling like that is 0. Photon with its electric field like that wiggling like that is 1. Photon with its electric field wiggling like that is 0 and 1 at the same time. So we've been building these quantum computers and quantum communication systems. I've been working, I myself am a theorist, so the experimentalists don't like me to use a screwdriver in their lab because I tend to break things, but I've been working closely with experimentalists for more than 2 decades now to build these devices. They started off small with a couple of quantum bits, but it turns out that just having a handful of quantum bits is enough to do good demos of the kinds of ideas of quantum computation. And now the quantum computers are getting a lot bigger. So now we have tens of bits, soon we'll have 50 bits, and we'll have 500 bits, because now there's a clear path to how you build a larger scale quantum computer. Well, classical computers famously obey Moore's law. It's not a law of nature, it's just an observation about technological progress where the size of the components in the computer gets smaller by a factor of 2 every couple of years, the number of components doubles. Now, quantum computers haven't been obeying a Moore's law. The reason is that actually to build quantum bits and to put them together is a difficult process. You're operating at the most microscopic scale. It's tough to do. You have to control things very, very precisely. And but there actually is a kind of a parallel Moore's law that goes along with the ordinary Moore's law. In fact, it's responsible for this, which is that as time goes on, we're getting better and better and better at controlling things at very microscopic scales. And the same ability to control things is allowing us to make more and more powerful quantum computers. Now, our quantum computers are still piddling compared with a classical computer. I remember I had a classical computer that had 16K of memory, and, and then a few years later it was 64K of memory. And now it's like 100 gigabytes of memory or a terabyte of memory. But quantum computers are still at the stage where we just have a small number of bits. 10 bits that we can use, soon 50 bits that we can use, 100 quantum bits that we can use. Still, even though this is piddling by comparison with a classical computer, because quantum computers for specific problems are so much more powerful than classical computers, this means that over the next 5 to 10 years, once we get up to something like, a few hundred quantum bits, which is going to happen soon, then we'll be able to solve problems you couldn't solve on a classical computer. So, what problems are we going to solve? So, a quantum computer with, say, 500 quantum bits, the kind we're going to see soon around the corner, would not be able to factor large numbers, break codes, and strike fear in the heartless NSA. But it would, however, be able to do some of these problems, for instance, like quantum machine learning, finding patterns in large amounts of data. Last weekend, I organized a conference on quantum machine learning at NIPS, this gigantic machine learning conference in Montreal. And we were expecting a few dozen people to show up, and there were 150 people you couldn't get into the room, because people in ordinary machine learning, classical machine learning, are always on the lookout for new ways of doing things. And they were very surprised to find that kinds of machine learning problems, like, for instance, looking at the topology of something, figuring out the number of holes in a piece of data. Topology studies whether things have holes or gaps or voids or connected components. These are features of the world that people who are analyzing data would really like to find. But the classical algorithms that do this, while effective, are only effective on very small numbers of holes, for example, because they just can't process that data. By contrast with a small quantum computer, even one with a few hundred quantum bits, you'd be able to find complicated patterns in topological systems like holes and gaps and voids that you could never actually find classically. So that's we've really progressed to a new stage. I mean, the first 20 years of quantum computing were very interesting ideas from theory, establishing connections with other branches of physics, coming up with different algorithms that you would love to perform if you only had a quantum computer that was big enough to perform them. And now we're on the brink of having quantum computers that are big enough to actually perform these kinds of analyses, do simulations of other quantum systems that no classical system could do, find patterns in data that no classical system could find. So I think it's going to be a very exciting time for quantum computation coming up. So who has quantum computers right now? Well, everybody's got quantum computers, over at MIT. There are, 5 or 6 laboratories with quantum computers sitting in them, and people are trying to expand them, make them bigger. There are hundreds of groups around the world that are building quantum computers. Yeah, so these quantum computers in these laboratories are pretty interesting. I mean, they look different according to what you're using. So, for instance, a superconducting quantum computer, whose quantum bits are supercurrent going forever around this circuit in a clockwise fashion, well, that's a 0, and supercurrent going around the loop forever in a counterclockwise fashion, that's a 1. And supercurrent going around the loop in both directions at once, which is kind of hard to imagine, but that's what happens. That's 0 and 1 at the same time. So there, the actual devices themselves in the guts of the quantum computer is a chip. It's a chip that's etched using relatively conventional technologies in which you etch these little superconducting circuits. Then the chip itself then is connected to wires that come in from the outside world. Because it's superconducting, it's got to sit inside a helium dilution refrigerator at 15 thousandths of a degree above absolute 0. So you've got this big thing that sits there looking like a beer keg going clickety click 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 as it cools it down. And then you talk to it using an ordinary computer. So you just type on your keyboard, it sends signals into the chip processes those signals, and then it does its weird quantum mechanical thing to get the answers out. I mean, these things are pretty large right now because actually really just because of the dilution refrigerator which contains it. You wouldn't want to put it on your lap because it would squish you. But they're sufficiently compact that you could actually just, have them sitting in your office if you like. For example, there is a special purpose kind of quantum computer, a quantum annealer that's made by D-Wave. This is actually a commercial device, and now a number of people have bought them. Lockheed Martin has bought a D-Wave computer. Google and NASA have bought them. The Army is buying some of them. And they're buying them because they're very interesting devices. Nobody understands exactly what's going on inside them. They're doing things that are quite mysterious in their own quantum mechanical way, because being mysterious is a quantum mechanical thing. And people are buying them to put them through their paces to see if maybe you could solve some hard problems on them that you couldn't solve on a classical device. These devices, this D-Wave device is actually based on a couple of papers that my graduate student Bill Kaminsky and I wrote in 2002, and we said, hey, you could take a superconducting chip, you could make a quantum annealer on it, the special purpose quantum computer, and here's how you do it. And we then didn't patent it because we were idiots. What could I say? Well, we didn't patent it because we actually knew from a simple analysis of our theory that this device wouldn't operate in the way that you wanted it to operate, which is staying in its lowest energy state throughout the computation. So, like fools, we didn't patent it. D-Wave went along and built it. They admit this freely. Why shouldn't they? There's no patent. And then when they built it, it was indeed true that it didn't behave in the way that you wanted it to behave, staying in the lowest energy state throughout the computation, got excited to higher energy levels, but it still solves the hard problems. Why is this? Nobody knows. I've been working with the folks at D-Wave to try to figure out why are they successful when they shouldn't be. And ever since then, I patent everything, by the way, even if I know whether it's going to work or not. So another fun kind of quantum computer are quantum computers that rely on quantum optics, on light. Now, for many years, these devices were massive because basically they consisted of a bunch of lasers, big lasers sitting on an optical table covered with a million mirrors, carefully aligned by graduate students so that all the beams of light were going in just the right fashion. And now there's been a really amazing development in this particular field, because based on techniques from telecommunications, people now can put the whole thing on a chip. So you take an optical table the size of a football field, and you can pop the entire thing, miniaturize it, and pop the entire thing on a little chip this big. And then the chip is etched with little lines of silicon, and the photons go zooming along these little lines, bounce into each other, bounce all around, interact with each other, and then come out the other side. So these are great devices and very fun to play with. One of the funky things about these devices is it's become clear over the last 5 or 6 years that even in some sense these devices should be very simple. It's just light moving through a chip, photons bouncing off mirrors and interacting with each other, that their behavior can be very mysterious. If you send, 20 photons into these little ports going into the chip, and you ask, well, what's the probability that they come out of these 20 other ports coming out of the chip? This turns out to be extremely hard to calculate classically. Nobody knows how to do it. Yet this chip can just do it automatically. It can generate patterns these patterns, nobody knows how you could possibly generate them on a classical computer. They have some kind of weird quantum feature that we can't generate, even using the world's largest classical supercomputers. One possibility for such devices for learning, for instance, is a common feature of machine learning is if you have a device that can generate a certain set of patterns, then it can also recognize the same set of patterns. So right now we're working on an experiment to try to see if we can make this happen. Can we have the patterns that are generated by one of these chips and then train another chip to recognize a set of patterns? If we can do that, then we'll have trained a quantum device to recognize patterns that couldn't possibly be generated or recognized by a classical computer. Yeah, we don't know. These patterns are so weird. You look at them, and they're, of course, because they can't be generated by any kind of classical object, they're like nothing you've ever seen before, by definition. In addition to having these funky patterns that we have no idea what they would be like, how you generate them classically, then quantum computers could do ordinary machine learning kinds of tasks, like just recognizing large-scale patterns in data, the kind of everyday thing that we now use all the time, things like facial recognition, voice recognition, character recognition, finding hidden patterns in data, so trying to figure out, for instance, a very important question if you're investing in the stock market is there some hidden dynamics that's driving all the stocks together in some pattern? If you knew what that dynamics was, then you could make a lot of money. And a quantum computer could find such patterns much more efficiently than a classical computer could. So there are plenty of ordinary kinds of problems where a quantum computer, even a very small one with a few hundred quantum bits, could actually do things that a classical computer couldn't. And then there are the crazier things like these patterns, that are generated by these devices that are never generated classically. I don't know what these patterns are good for in terms of recognizing them, but they are very useful in terms of problems that involve cryptographic applications. For example, just encoding information in ways that nobody can actually decode, because if you take your information, you put it into one of these patterns, you put it together with one of these patterns that nobody can decode, then by gum, nobody can decrypt your information. It's useful to compare the current state of quantum computation and what's been going on with the last 20 years with what happened with digital computers over their first 20 years. So the idea of building a digital computer was proposed in the mid-1930s by Claude Shannon, and actually as part of his master's thesis at Harvard. It was a very influential master's thesis by Konrad Zuse in Germany. And the first devices started to be built then, effectively, in fact, during the Second World War. And by the mid-1950s, then people had these gigantic, extremely expensive devices. There were very few of them. They cost a lot to build. It was a huge effort for a very small number of bits. They break down all the time. So the idea of building a quantum computer was something that I proposed in 1993, and quite soon after that, people started building simple quantum computers, and it's been tough to do, just in the same way the first 20 years of building classical computers was tough. And now we're at the stage where we have these quantum computers that fill rooms and have, lab technicians in white coats tending to them. They're hard to operate, they break down, and they still only have, a few tens of quantum bits, though of course we're making progress. So what's interesting about this is, there is, with computers, there's this, if you build it, they will come. So I have many senior colleagues at MIT who were participants in this early days of computation, people like, Marvin Minsky, Bob Gallagher. And these, when they tell me about, the good old days, which they're fond of doing, one thing that comes across was the origins of computer science in the 1950s was tremendously exciting. And there was a huge change as soon as they actually had a device that they could run their algorithms on. Even a device that was, a huge device physically, but incredibly weak and puny by comparison with today's standards. So pretty much as soon as people had developed the first computers where they could actually run programs on, within a few years, these pioneer computer scientists, wasn't even called computer science at that point, they'd actually developed, many of the most powerful methods that we know today, things like Monte Carlo, simplex algorithm, all these algorithms that people now use for everything. It was a tremendously exciting time. And it was exciting because all of a sudden, these really smart people who'd been kind of working in the realm of theory had a toy they could play with. And very fast, they came up with a huge number of fun games that they could play with this toy. It was a pretty expensive toy, but there were a lot of fun games they could play on that. The field of quantum computing is in that stage right now. We have these toys, these, simple or, complex, not so powerful quantum computers, but we can play games on them. And we can try out the things that people come up with, and we can see what happens. And people are coming up with very fun games. As a result, the field of quantum computing is tremendously exciting for someone like me, because it's full of young people with fantastic ideas. Some of the most brilliant young scientists I know in the world have gravitated to this field because it's fun. You can play awesome games. The questions are big. You can ask questions about, the nature of the universe. You can ask questions about, can I recognize a scrawled 5 or 7? But then you can actually work with people, so you can say, hey, I've got this idea. Can we try it out? And, you walk down the hallway at MIT and somebody says, yes, we can try that out. Let's see what happens. So the field of quantum computing right now is a tremendously enjoyable place to be, just from the point of view of intellectual play. And, for me, it's great because I get to work with these people who are a heck of a lot smarter than I am, and that is a lot of fun too. Thinking about the future of quantum computing, I have no idea if we're going to have a quantum computer in every smartphone. We'd have quantum apps or QAPs that would allow us to communicate securely and find funky stuff using our quantum computers. That's a tall order. I think it's very likely that we're going to have quantum microprocessors in our computers and smartphones that are performing specific tasks. This is simply for the reason that this is where the actual technology inside our devices is heading anyway. And if there are advantages to be had from quantum mechanics, then we'll take advantage of them. Just in the same way that, in photosynthesis, the stuff, the energy is moving around in a quantum mechanical kind of way. And if there are advantages to be had from some quantum hanky-panky, then, quantum hanky-panky it is. So, of course, it does. One should always ask with these technologies, is it really worth it? Right? Is the internet worth it? Yeah, probably it is. On the other hand, there's a, there's a huge amount of stuff that's not worth it on the internet. Is it a great thing to have a smartphone? Sure, on certain occasions it is. A lot of time it's just a distraction, however, that prevents you from paying attention to what's going on around you. Makes you run into lampposts while you're texting. As a professor at MIT, and I'm a professor of mechanical engineering, quantum mechanical engineering, I'm exposed to novel technologies all the time. Most of them, super cool technologies that will never be turned into something that people will be used, but they're super cool nonetheless. And the strategy I've learned with this is, there's a huge number of technologies out there, and you just don't have to adapt them. You have to, or adopt them. You don't have to adopt these technologies. You don't have to use it. You can use the ones that you like. You can not use the ones that you don't like. So, for example, I don't use Facebook or Twitter or other social media because I feel that there's presence, and then there's absence, and then there's cyber presence, and cyber presence is a heck of a lot closer to absence than it is to actual presence. Similarly, when I look at my parents and their friends, they have friends who are people whom they go and visit. They go stay overnight. They have dinner together. They talk with them. And, that's what a friend is. And maybe some of your friends on Facebook are friends like this, but probably not most. So I think, most of the things that make human life rich and rewarding are just about being human and not about technologies. If we're lucky, we can find a technology that helps us understand what's going on better or useful for certain purposes, and that's great. We should use those. Of course, a lot of these technologies get used for, for bad, sloppy, annoying purposes as well. In general, I would say that, that if we're lucky with a technology, if you here are the good things, here are the bad things, and the average is just a little better than, zero, and that's good. Technology is not neutral. I mean, in fact, one of the primary uses of technology, just very naturally in the way that the economy works, is that wealthy and powerful corporations use technology to exploit ordinary people. I've experienced this a lot just in my own job. When I started off as a scientist, I would write, I spent most of my time calculating by hand and, writing formulas on blackboards. And when I wanted to write a paper, I would maybe type it up or write it out by hand, and I'd give it to someone who would type it, and then it would go to a journal, and there'd be a typesetter at the journal, and the journal would type in a very skilled job to typeset scientific equations. The typesetter would typeset these scientific equations, and now what happens is when I submit a paper to the journal, I have to typeset it myself. I mean, there's a very nice program called TeX or LaTeX that allows you to typeset scientific equations, but it takes a lot of work. I'm spending a lot more time to write a paper. I spent a lot more time than I did in the past, and a bunch of other people lost their jobs. Yeah, well, this is one of the very natural things about technology is that at the same time it makes some jobs more efficient and easier to do. It means that the people who are actually doing them end up having more work because your employer is making you do more stuff. And then there are a bunch of other people out there who are out of a job. So technology is not neutral. I mean, it can make things more efficient, but it doesn't necessarily make our lives easier or better. In fact, it often makes a lot of us work a lot harder, which I object to. Well, I find it's easiest to tell people the truth about what's going on, and that's good for them too. There are a number of Fortune 500 companies that are investing heavily in quantum computing. IBM has always been heavily invested in quantum computing. Microsoft, Google, now Intel is making a very significant investment in quantum computing. NEC in Japan has a big investment in quantum computing. So there are quite a few companies that have decided they want to invest in this field. And now when they ask me, okay, are we going to have a quantum computer that we can build and sell to people soon? I say, well, maybe not, though actually we're much closer now. And in fact, I think it's quite likely with these new advances in the technologies, particularly of things like superconducting quantum computing and atom optical quantum computing, that we will have quantum computers that people can build and they might be able to sell. But there's, I think, a very good reason for such a company like Google or IBM, or Microsoft or Intel to invest in quantum computing. And that is, this is a technology that has tremendous promise, even though at the moment it's not something that is incorporated in everyday's smartphone. And the reason has to do with the nature of computing in general. And when people first built these humongous computers the size of a gymnasium and put them in gymnasiums, they really didn't have the slightest clue about what computers would be used for. And they were thinking, oh, we'll do it, to analyze things like shell trajectories, some material properties and things like this. But one thing that we've all experienced over the last few decades is that computers can do things that you would never thought they would have been able to do. And moreover, information processing technologies have exploded in a way that nobody would ever have expected. So now it really doesn't make sense to just talk about computers, because everything is computing. I mean, your smartphone is a tremendously powerful computer. Your car engine contains, 20 to 50 microprocessors that are computing away all the time. And this is the secret for actually getting much better fuel efficiency with pollution controls, etc. It also turns out to be the secret to cheating when pollution controls. So computation is present, and information processing is present in a huge number of devices. And it's this notion that almost anything you touch is capable of processing information in a sophisticated fashion. This is now a commonplace. So if you're a company that deals with questions of information processing, then it's very important for you to know what's going on. So places like, for instance, IBM's very long-term investment in quantum computing, they've been strongly invested in quantum computing from the beginning, basically for more than 2 decades. That comes because they had very good people who were amongst the founders of the field who were developing it, Rolf Landau and Charlie Bennett. And it was clear that really amazing things would come out of this. So it's not like they're investing, $1 billion in quantum computing, but they're investing tens of millions of dollars a year. I don't know what their actual investment is. And as a result, they have some of the best and brightest people who are in the world who are working with them, who are coming up with the ideas, who know what's going on, who are playing with their own quantum computers that they're building. The same is true of all these other companies. They're fantastic places for young people to work, and they're some of the main places where new ideas are being developed. DARPA has always had a close relationship with quantum information processing. By its very nature, program managers at DARPA are always wanting to, hit it out of the park. And it's been clear from the beginning that quantum computing is potentially a technology where you could hit it out of the park. I was part of I was a co-principal investigator on the first quantum computing grant from the government, which came from DARPA back in 1994. Jeff Kimball was the leader of this group. And, DARPA realized right away this is something that they could look at. And in fact, over the last 20 years, there have been a wide variety of programs at DARPA investigating different aspects of quantum computation, many of them very successful. I think a lot of the fundamental advances in quantum computing have ended up being funded by DARPA in one form or another. It's not always, as usual with DARPA. I regard this as a good thing. I'm not sure if the head of DARPA regards this as a good thing. Frequently, what ends up being developed by a particular program is not what they set out to do in the beginning. But it turns out that there's some spin-off that comes out of this program that is tremendously powerful. For example, DARPA was the first funding agency to recognize that this role of quantum mechanics and photosynthesis was a very important thing. And they created the first program to fund looking at funky effects like quantum coherence and entanglement in photosynthesis and in energy transport. It was a very successful program that had wonderful results from it. And right now, with some of the spin-offs that came off that I'm working on right now are these man and woman and virus-made systems that are much more efficient in their energy transport than anything that's found in nature. So, yeah, I mean, DARPA has its fingers in many pies, and it's got its fingers in many quantum pies, and it's been part of developing many of the fundamental ideas in quantum computing. And in fact, when IARPA spun off of DARPA, IARPA has also taken a major role in investing in the forefront of quantum information processing. Because it's grown so rapidly, and because it has impact on so many other fields, there are now a lot of subfields in quantum computation and quantum information processing. There are the techie guys who are building quantum computers, and of these there are some really remarkable people out there in superconducting quantum computers. John Martinez, who has just been hired by Google, my colleague Will Oliver at MIT, the group at Delft. Then there are people who are looking at wild-eyed and crazy ideas about what kinds of new quantum algorithms you could come up with. Scott Aaronson, my colleague at MIT, the famous blog poster on Shtetl Optimized, he has a remarkable set of ideas, and he and his colleagues are mapping out the set of questions that you might be able to solve on quantum computers, and doing a wonderful job. In one of the most successful and powerful types of devices you can make to build a quantum computer out of is using ion traps, where you take a bunch of ions, atoms, you strip electrons off, you trap them in a little trap, zap them with lasers. My colleague Chris Monroe at University of Maryland is a pioneer in this field. Rainer Blatt at the University of Innsbruck has done amazing things on this. My colleague Ike Schwang at MIT too has made lots of progress on building these devices. My favorite part about quantum information is the kind of wild and crazy stuff where we say, hey, let's understand how the universe is made and how it's put together, from thinking about it in terms of quantum information. So thinking about quantum gravity, which is something nobody understands, in terms of quantum information, is something I've been doing now for 15 or 20 years, and now there are quite a few people working on this. It's quite fun. John Preskill, senior people include John Preskill at Caltech and Alexei Kitaev, who's a MacArthur Prize winner. They're both brilliant people making great strides in this regard. As I said, one of the things that characterizes the field of quantum information is the tremendous quality amongst the younger researchers in the field. Patrick Hayden, who's just been hired at Stanford exactly to look at questions of quantum mechanics and quantum gravity. Brian Swingle, who came up with one of the main connections between quantum gravity and quantum information when he was a graduate student at MIT. All on his lonesome. Let's face it, the guy is brilliant. What can I say? China is a bit of a latecomer to the quantum information game, though they have, about 4 years ago, they established an institute for looking at quantum computing at Tsinghua. And this is an excellent institute, and they're doing great things. And there have always been some wonderful individual experimentalists in China doing quantum information, like Pan, for example. Singapore has an amazing program in quantum information processing at the National University of Singapore. It's one of the leaders in the field. There are many fantastic researchers in Japan on quantum information. My colleague Yasunobu Nakamura, and groups at Tokyo Institute of Technology. NEC has always had a great group there, and there are many great people there. The largest group of collection of people, concentration of people working on quantum computation are actually in Canada at the Institute for Quantum Computing in Waterloo, where Mike Lazaridis, the founder of BlackBerry, has donated hundreds of millions of dollars as seed funds to create a remarkable group of researchers headed by Raymond Laflamme. And this is, in some sense, this is the the biggest concentration in the world these days. There are many fantastic quantum groups in Europe. The University of Vienna has amazing people. Anton Zeilinger has been there for a long time. Philip Walter there. The Oxford and Cambridge have great programs with Vlatko Vedral at Oxford, Richard Joza at Cambridge. Oh, and of course, David Deutsch at Oxford is, founder of the field, though it's difficult to see him because he only goes out at night. Yeah. I've had many conversations with David Deutsch over the years. One of the most fun conversations was when I was running a session at a conference at MIT, and David was appearing by a video link, and I was in this gigantic auditorium with a 40-foot tall screen in front of me, and I was seated in the front row of the auditorium, and David's 40-foot tall head was talking to me from the screen. There was nobody else in the room, and we were just talking about physics. It was like talking with the Wizard of Oz. David is a brilliant person and a deep thinker. I don't really need to say it, but it is true. He was the first person to realize that quantum computers could do something really fundamental that classical computers couldn't. And it's interesting, he realized this in the mid 1980s, and it took him a long time actually to come up with an example of something where a quantum computer could do better. He had this intuition. He came up with the kind of formal notion of a quantum computer, but for about more than 5 years or so, he couldn't come up with something where it could do better. And then when he finally came up with something, he showed, well, here's something where a classical computer takes 2 or 3 steps on average to do this problem, and a quantum computer can do it in 1. So even that wasn't, it was an advance, but it wasn't, a problem that anybody would like to solve. But he was so fixed on the idea of coming up with the idea and figuring out what you could do that in the end, he kind of, by sheer force of intellect and willpower, brought the community around to realize this was an important thing. And then, so other people started working on this and coming up with ideas that could be more useful. The quantum Fourier transform that finds periods and functions, and then Peter Shor uses to come up with his famous algorithm for factoring numbers and breaking codes, and then it was off to the races. Now, during the last 2 decades, since in the kind of, the renaissance of quantum computing, since Shor's algorithm in 1994, it's gone from a half dozen people in the field to thousands of people in the field working on a vast variety of things. During this entire time, David has, stuck by his own lights, and he's continued to work on what he regards as the most important things. For the last 10 years, he's been working on what he calls a quantum constructor theory, where, so far as I can tell, and I can't say that I understand it very well, he's trying to derive the very nature of reality from ideas based on quantum computing. And I wish him good luck in doing so.